Well, yes, welcome everyone to GeoHug. So, before we kick off today's session, I'd just like to take this time to acknowledge the traditional lands which we're all coming from today. I live on the beautiful lands of the Gadigal of the people of the Aurora Nation, and I'd like to pay my respects to the elders past, present, and future. So, Jon Furlong has spent a decade processing, interpreting, and managing commercial microseismic projects. He did this work initially at ESG Solutions for oil field operations. And in the past 4 years, Jon has been working with fiber optic systems, specifically DAS for microseismic and strain monitoring. So now with Silixa, Jon is excited to bring DAS to challenges in the mining industry. So I'm excited to have him on today to discuss distributed fiber optic sensing and its applications for imaging and Rockmass response monitoring in mines. So it's going to be a great session. I hope you all enjoy it. Please use the chat and we'll be opening up the floor at the end. And yes, thank you so much, Jon, for joining. It's wonderful having you.
Awesome. Thank you so much, Jessica. The title of this talk is called Distributed Fiber Optic Sensing and its Applications for Imaging and Rockmass Response Monitoring in Mines. So I'll start this talk about distributed fiber optic sensing first, and give an introduction to the technology and how it works. And then I'll talk about distributed acoustic sensing and compare standard versus constellation or engineered fiber, and use a case study from underground mines for that. I'll discuss imaging using DAS and use some brownfield exploration examples from Finland and what we can do in the future with DAS in mines for imaging. And then move to microseismic monitoring and discuss microseismic monitoring and the benefits of using DAS for microseismic monitoring and all the applications there. And I'll show a case study from a preconditioning example in a mine, and then discuss strain and microseismic monitoring and some of the advantages there that DAS has, and then summarize it all in the end. So what can fiber optic do? So fiber optic can do quite a bit in our mine. So it can measure everything from the absolute base of our mine to the surface of our mine. We can measure things like strain, microseismic, temperature. We can do VSPs, vertical seismic profiles for imaging. We can do 3D tomography work, passive or active. We can measure ostriches at the surface. But how does the technology work? So essentially, fiber optic works. It's laser that's attached to a fiber optic cable. So the fiber is the sensor, and it's going to fire that laser very quickly, and it's going to pulse light down the length of the fiber. And if you know what the refractive index inside your fiber is, and you know what time you pulse the light, then you know, and when you receive a backscatter response at your interrogator, you can assign every point along the fiber as a sensor, essentially. So if you know you have velocity, you have time, so you can calculate the distance for every backscatter response along the length of your fiber, and thus you turn the fiber into a distributed array. So the benefits of distributed sensing, you can see here kind of in the bottom left. So here's just an example of a response being sampled here by point sensors by these dashed lines, and you can see how it's kind of a smooth curve. For a distributed sensor, we can see much higher resolution spatially. So something like this here at point C, where you have a dip in your response curve, distributed sensing is really useful at being able to detect those small changes in your signal. So we can turn a fiber that's 10 kilometers long into 10,000 small sensors along its length and have a point measurement for every one of those sensors. So it gives really high spatial resolution. But what are we actually measuring? So there are 3 different backscattering phenomenon that we use with interrogators. So the first and the most common that has been used for some time is Raman backscattering. So Raman backscattering is used to measure temperature, and it's been done for many years. So that's very proven technology, and we use it quite a bit to this day. But mostly what I'm going to be talking about today is going to be DAS and strain specifically. So we can measure absolute strain with the Brillion backscatter response, and then relative strain and acoustics we can measure with the DAS backscatter response. So that's distributed acoustic sensing. So distributed acoustic sensing has improved a lot in the past few years. So what was normally difficult to do to measure acoustics, now we've been able to lower our noise floor and see a lot more. And we can also use engineered fibers and kind of finely tuned systems to further decrease our noise floor. So when we measure a backscatter response with Rayleigh backscattering, we need a small strain rate in the fiber that creates a reflection that we measure at an interrogator. But by engineering the fiber, we can create signal by having a smaller amount of strain being experienced on the fiber to create a backscatter response, and that in effect just lowers the noise floor. So that's really important for things like microseismic monitoring where you're not going to have the benefits of stacking in signal over time. You're going to have a discrete signal that you only measure once, and if you don't see it, you don't see it. So having a high fidelity system is really important for those applications. So discussing more about fiber optic sensing and DAS specifically here. So DAS is a full waveform sensor. So just like a geophone, it can measure frequency, phase, and amplitude. And you can see an example here from a downgoing wave for a vertical seismic profile. So this is the direct wave arrival. And you can see it overprinting on these blue little squiggles here on the DAS signature. So this is depth on the y-axis and time on the x-axis. You can see the geophone response and what it's sampling. And then on the left here, you can see the geophone response in red and the geophone response in blue and the DAS response in red, and just how those signals in frequency and amplitude and polarity match each other really well. Just kind of emphasizing that point that for many of the applications that you can use a geophone, you can use a DAS array, and then you can extend that DAS array to 50 kilometers or more with that dense spatial sampling of 1 meter, or even greater in some cases, up to 25 centimeters. And also DAS and fiber is really suitable for harsh environments. So you can use it in, we have fiber optic arrays measuring acoustics on the top of glaciers, and we have it in deep wells in the Permian, over 100 degrees Celsius. And the equipment can acquire in those environments for years without any issue. So once it's installed, it's pretty robust and it doesn't need much maintenance. So moving on, so this is some seismic imaging work that was done between NRCan, so Natural Resources Canada, and New Afton Mines in BC. And so in this project, they were looking to do a vertical seismic profile in the subsurface of their mine with two kind of semi-short borehole. Well, they're 800 meters or so they're not short, but they're looking to image lithological contacts and fault zones that act as mineralization for alteration zones. So you can see the boreholes over here and kind of a schematic of how we've placed our fiber in these boreholes. So essentially, we can do turnarounds in our fiber at the base of any individual borehole. So we place the fiber in these boreholes that are roughly 800 meters in length, and we do fusion splices at the surface so that we can daisy chain multiple boreholes together and make one continuous array. So one interrogator can then sample many, many boreholes, and many kilometers of fiber in that method. And the results for this were quite good. We wanted to compare in this example engineered fiber versus standard fiber, so that we can see what the response is and how useful it would be for subsurface applications. So you can see the constellation fiber or the engineered fiber on the left, and then the standard DAS fiber on the right. And you can really just the difference here between the noise floor. This is the direct arrival from a 1 kilogram of pentolite explosive was the source, but you can see the differences in the noise floor and the signal that you can see in the engineered fiber. So it's a really high resolution system. So it's quite a successful experiment for that. And you can see here, this is one of the initial trials of the Carina system, of the high fidelity system. So our team kind of working in the subsurface in 2017 in a tent where these boreholes were instrumented, and you can see all the equipment down here. So overall, a really successful experiment, and it produced great results. So moving on, kind of continuing on in that theme here. So how does that help us in mines for imaging and for exploration? So this example here is this is Kylylahti mine in Finland, and so this is a sulfide deposit here in pink or in red here that you can see. So what they were looking to do was do a VSP experiment using a number of different shot points, and then they used their boreholes and image their ore body. So they had a mine model, and they wanted to compare the mine model. They generated a synthetic. They wanted to compare the mine model to what kind of reflections they saw on a geophone array and a DAS array. So these boreholes were roughly 500 meters each, and each one was instrumented with geophones. But they also instrumented the 917 here with fiber. And then, all these shots here you can see in green. And then they did their experiment and recorded results and processed for the reflectors and compared them to their mine model. So on the top right, you can see this is the geophone data here that was processed. And then this is the DAS data below that, in the bottom right. And this is all the individual reflectors that have been identified and their mine model ended right about here in the orange line. So the general consensus from the experiment was that DAS and geophones actually do a pretty comparable job when it comes to imaging quality for a lot of the mine ore body. But in some circumstances, for far field reflectors, DAS will actually do a better job of imaging, and that's because DAS is as capable of using the full aperture of the borehole. So a lot of these far field reflectors that you normally wouldn't be able to see, you're able to see because you're able to capture this larger aperture with a DAS array. So this reflector here, reflector 11, out to the west, they actually don't know what that is fully. So the authors of this study, kind of their summary was that by using fiber optic, because fiber optic is so cheap, the cable itself is very cheap to deploy and easy to deploy, that you can substantially kind of reduce exploration costs by using a lot of fiber in your mines, because you could just, when you're drilling these exploration boreholes that are part of your process, you can instrument them with fiber for very little, and then when you want to come back to them, you can turn them into arrays that you can use for imaging or for microseismic detection. So there's a lot of different applications that you can use these boreholes for, and it should save costs and time for exploration. So moving on now to talk about microseismic monitoring with DAS. So this is a 2,500 meter borehole example of a unprocessed Carina event. So high resolution microseismic waveform rolling across a fiber optic array, and what that signal quality looks like. So it shows this example here. You can see a P wave arrival at the apex here, really strong over the full lateral here. You can see the S wave arrival, but you can also see great detail here, like reflected waves, S to P conversion. There's a lot of data that we can see in fiber optic that we normally wouldn't be able to see with a geophone based system. Comparatively, a geophone system, if you were to sample here, you might have a geophone here, here, here. You might capture the P and S wave arrival, but you're just not seeing that full move out. And there's a lot of data that's contained in that signal that we get on DAS. And for those of us who've processed any amount of microseismic events, we know how susceptible we are when doing microseismic event locations to the velocity model uncertainty, especially in mines when we have really heterogeneous velocity models. So we oftentimes just kind of have to go with a static velocity because they're so kind of dynamic and changing that we can't always be updating them. So what we can agree on here is that with more sample points, is that you're able to reduce your location errors by using all of that aperture in your location. So opposed to a geophone that kind of does a time residual optimizer by using the P and the S wave arrival to ray trace an event location. Here you can use your P wave alone to locate an event, your S wave alone to locate an event, your P and your S together. So it just adds a lot more resolution to the hypocenter location. So continuing on with fiber successes and challenges, more specifically DAS, I should say, successes and challenges when it comes to microseismic. So this example here, just we already kind of harped on about in the last slide, which is that location accuracy. So this is an example from Xin and Yi from CSIRO. They use a standard IDAS to record this data in a longwall coal mine. So the borehole was 300 meters deep, and they had 3.5 kilometers and a fiber that they draped across the surface. And what's cool about this is that they were actually able to, they can see their S wave arrival. And then in this circumstance, they don't even need to calculate a velocity model or use a velocity model. They can just pick an apex of your event of the arrival and then draw a line in space and pretty much locate that microseismic event without having need of a velocity model. So again, with high resolution and lower or lower location errors when you use a DAS array. So source parameter calculations is something that is kind of in the works with DAS. So fundamentally, geophone, a DAS array is not a geophone array. Both can be used to calculate source parameters. Geophones have been around for a long time. If DAS was around in the 60s, then maybe we'd be using all of our equations we built on fiber. But in this circumstance, there's a non-trivial kind of shift that we have to use when going from strain rate with a fiber to displacement, like a geophone measures in velocity space, and then they integrate to get displacement and do a Bruin magnitude fit. But that's kind of the point here. The point is that when we look at geophone data, so this is an example from Ariel Lelouch, who used Forge data, which is a Utah geothermal project where they had geophones and DAS. And he was able to calculate the magnitudes for both the DAS and the geophones, and he just did a little regression to see how good the fit is, and it was quite high. So we're doing good work, and so this work was done a few years ago, and we're doing some good work now too to show that the relationship between geophone magnitudes and DAS magnitudes are quite close. And it's mostly that spectral plateau, and once you kind of get your Broom magnitude fit, like all of the apparent stresses, static stress drops, total radiated seismic energy, corner frequencies, and source radius, and things like that kind of all fall into place. So that's very close. We're hoping to have some solid source parameter calculations soon. And finally, moment tensors. So really important for mines to understand, what is the source mechanism of their event? Is it the rock that's hitting a crusher? Is it kind of an explosive source? Is it a cave back that's propagating upwards? Is it an implosive source? Is there some sort of shearing event that's going on somewhere else in the mine, maybe near a fault? That's important to know. So understanding what your focal mechanism is important, and moment tensors, and DAS can help us get more resolution to our moment tensors, because it's able to sample the full, get more of that that focal mechanism captured in the move out of the waveform. So here you can actually see how the transition in the signal goes from negative to positive and positive to negative on the S wave as it kind of transitions across a focal sphere. So in the future, we can use that data to help add resolution to our moment tensors and have more certainty with those values. So moving on now from microseismic and starting to move towards imaging and tomography work. I wanted to show an example here just so we can visualize how geophone arrays compare to DAS arrays when it comes to sampling and how much they sample in space. So I used 2 boreholes that are roughly 80 meters long, and I have 3 hypocenter locations. So if we have 8 sensors, so if we instrument the boreholes, those 80-meter boreholes every 20 meters with geophones, so we're gonna get a total of 8 sensors. And then if we ray trace through this velocity space, so this is just a continuously increasing velocity space, then we're going to see a total of 24 rays. But now in purple, if you were to instrument the entire borehole with fiber, that means every meter of that 80-meter borehole becomes a sensor. And then you have 160 channels in total between 2 arrays. And if you ray trace through that space, then you get 480 rays. So just a lot more sampling, in this case, 20-fold increase in sampling. So that's really useful for some of the tomography work that mines are doing now and adding resolution to that. So this is an example from Rocksigma. So big thanks to Rocksigma for letting me use this example to kind of illustrate the benefits of tomography and how fiber can help add resolution. So in this example here, they had this is the Garpenberg mine from Sweden. So this is tomography work that they did, that Rocksigma did, and you could see that the geophone locations here as triangles, and then the microseismic event cloud around their excavated ore body. So using those microseismic events and the geophones, they were able to invert for their tomography. So this is their P wave velocity model through the mine. So it's kind of doing an MRI of the mine itself. And you can see where those values turn to deep blue. That's where the P wave drops to 0, kind of correlates to where that rock mass has been excavated. And then how those cubes and how those cells then change, their P wave velocity changes around and bends around the excavated ore body. So the thing that I want to show here is that, this was done with geophones, but if a borehole was nearby, or if any of this amount of this area was instrumented with fiber, but if you had a borehole nearby that was sampling over this full vertical kind of space, and you can see this is where the geophone arrivals would be here with P and S wave arrivals for those 11 sensors. But if you had a DAS array, you'd be able to sample so much more in the space in between and just had that much more resolution. So what that means is that for mines that don't have a lot of seismicity, and there are a lot of mines we in conversations that they don't have a lot of seismicity, and kind of seismicity slowly increases with mine age. So they can't do a lot of these models because they don't have enough data. So if you have a DAS array, you're able to get more sample points. So you'd be able to do these tomographic models with fewer data points Or alternatively, you could do a higher resolution model, because for the same number of data points, you'd have much more ray pass. So you'd be able to get each individual cell size quite a bit smaller. Or in addition to that too, you could, because you have to get a certain critical mass of events before you can do a tomography workflow, you should be able to do that in less time, because you have more ray pass again. So you could do these maybe every couple of weeks, opposed to having to wait for a few months for the data. So moving on to Rockmass preconditioning, and some more microseismic here. So preconditioning in mines is becoming more and more common, where we want to drill short boreholes and inject and break down the rock mass before it's kind of produced. So in this example, this is from an iron ore mine overseas, where we installed a fiber optic cable into 4 different boreholes, and we daisy chained them through. So in and out of each borehole. So these were 25 to 30 degree dipped boreholes. So the fiber goes down and then it comes back up. We fusion splice it at the surface and it goes down and comes back up, kind of just like the new Afton example from the beginning. And then we interrogate it all with one fiber, or with one interrogator. So in this example, they injected for a couple of days here to precondition the rock mass, and we detected a total of 5,000 events. So it was a big success, and we kind of came back and did another 5,000, or another injection program with similar kind of data results a month later. But what I want to focus on is that understanding the microseismicity associated with these preconditioning programs is really important for understanding the efficacy of that hydraulic fracture, because you can break down the rock, but you don't know how far your fracture network is spinning. So by using microseismic, you can actually kind of draw an envelope around the space that has been released seismic energy. So you have an idea of how much rock mass you've actually stimulated. So this is an example of a microseismic event too that was recorded during this program. It's a little bit more noisy than what we would like. This is using our more traditional IDAS system, not kind of like the flagship engineered Fibre and Carina system. And these boreholes were not cemented in. So if the boreholes were cemented and you're using a higher fidelity acquisition system, you'd get that much more events, much more than 5,000. But we also saw a fracture hit on this project as well. And fracture hits are really neat. These are something that are very unique to DAS, and it's because DAS has a flat system response all the way to DC. So what that means is that where geophones have a difficult time measuring below 15 hertz or 10 hertz, DAS can record all the way into the subhertz bandwidth. So these small tension and compression along the length of our fiber, we can see all of that. So a fracture hit here is when you have an injection at a given depth here on the y-axis, and then you have time on the x-axis. So at time, 1,000 here, 1,000 seconds, you have a fracture front that's propagating from your injector to your monitoring borehole, intersects, and then you're seeing this tension and compression in the fiber as the fracture front moves past it, and then eventually shuts down. You can actually see in this case, because these are open boreholes, of fluid migrating up the borehole as well. So more on strain here in the next slide. So we use strain monitoring to great effect in hydraulic fracturing operations in oil and gas. So then this example here, you can see this is a borehole or a well that's being injected at a given depth. And we have a fiber optic cable in the northern well, just above that. And then over the course of 3 hours, you can see that fracture front propagating towards the nearby monitoring well, and then the strain effects on that well. So in the red here, that's when the fracture tip is kind of approaching the monitoring borehole, and you're seeing tension in the fiber. And then as the fracture tip progresses across the fiber, across the monitoring borehole, you're seeing tension and compression, that push and pull and the squeeze on the fiber. And then eventually, when the treatment program's over and they shut down the pumps, you're seeing that relaxation. So this is just kind of giving you an appreciation for like the fidelity of the system and all the capabilities of DAS and what it can measure. And then on the next slide here, I'll just kind of show how we integrate these things together and use all that data in a few plots. So, and this is an example here. So on the top left, example from oil and gas, but for a hydraulic preconditioning program too, or hydraulic fracturing program. In the Permian. So we have some on the top left here, we have some strain on both of these monitoring wells. And we had the strain, and then we have below this is temperature, because we also monitor for temperature during this program, and then some sample pump data here. But all I wanted to show here is that, as you stimulate the rock, you can see the microseismic events being plotted in these small dots, and then these are the strain events here being plotted alongside. So this is the more energetic seismic events that occur as a result of the injection program, and then these are the fracture hits and that strain hit on the nearby fiber, monitoring fiber. And then we can also plot this data on top of the strain data as well. So we can get an appreciation for how some of that more elastic response in the fiber and how it correlates to some of the seismicity that we're seeing and where it doesn't correlate, because sometimes it doesn't. But I feel this is going to be very useful for mines, and we're seeing some great results already that can't be shown, but looking forward to using this for understanding how mines propagate and how block caving propagates. So on the next slide, I'll kind of show how we plan to incorporate that all together in mind. So what does a full integrated solution kind of look like? So in this example, I'm using a block caving example, and please excuse the crude PowerPoint graphic here, but so there's different ways we can monitor a cave as it's progressing, our block caving operations. So we can put boreholes directly into our ore body itself with turnarounds and make one kind of continuous array, and we can measure from there. We can instrument boreholes outside of our target ore body. So those will stay for the life of the mine and be able to monitor strain and microseismic during that time. And then we can monitor the preconditioning program as they break down that rock mass, and then subsequently as it's produced, and that cave back propagation over time. And then for the boreholes that are inside of the cave, here you can see how they are. So this is commonly what TDRs are used for now. So these are just fiber optic cables that are measuring the breakage to monitor where the cave back is propagating over time. But if we're to use fiber in these examples and monitor for microseismic and for strain, you can not only just measure the yielded zone where the fiber breaks, that's kind of what typical TDRs do today, but you could also use the fiber to measure the seismogenic zone to see how much seismicity is propagating or is occurring as the cave progresses. But most importantly is probably the elastic zone. It's where you're having this kind of aseismic deformation that occurs ahead of your cave back propagation. And what we're hearing from different mines now too is that they can see this, and when they've used DAS and they've used strain, is that where they're seeing a strain response or an elastic response in certain areas on their fiber is where that cave back is going to move next. So it acts as an early warning sign to where the cave back is propagating. And if your ore body is not properly breaking down or breaking down outside of its plan, you'd have an early warning sign by using the measuring that elastic response or that strain response. So this is kind of like the final slide here, and this is just something that we're looking to do and we're doing right now in Kazakhstan. I can't show any examples of it yet, but subsidence monitoring is something that I think is going to be the applications for fiber and subsidence monitoring is going to be really interesting in the future because these zones are somewhat unpredictable and they're hard to measure, and it's hard to see as they propagate. So right now, obviously they're kind of closed off. But if they start to behave erratically, it'd be great to know ahead of time how that subsidence zone is propagating. So we could instrument fiber in the top left here, just kind of across your subsidence zone. But obviously, as that subsidence zone breaks away here and subsides, you're going to lose that fiber. So you could also try to do a more of a cinnamon bun type pattern, and that way, as the subsidence zone kind of lets, you're able to maintain fiber on the periphery. And so that way we can image hopefully some of these subsurface kind of tension cracks and fractures and things like that ahead of the subsidence zone. And we've actually had success not in, for an example here is from offshore California, where they had an ocean bottom seismometer, 15 kilometers off the coast. that was down for maintenance, and it was connected to the surface with a fiber optic cable. So when it was down for maintenance, we interrogated that fiber with the DAS unit, and then we were able to map all these these faulted zones that were otherwise unknown to be there, because we just have that higher amount of spatial resolution. And the source for that was just microseismic events or seismic events coming in off the coast and rolling through. So similarly, for a mine environment with fiber, if you had microseismic events occurring deep in your mine and they're kind of propagating through the rock mass, you'd be able to use those to help image different fractures in the surface, and maybe how you can see changes in the velocity structure over time. And there's also applications there for multi-channel analysis of surface waves if you're just looking to get that shallow velocity structure. Fiber has been really successful in doing that. So the last slide I have here is one of the elephants in the room with fiber, is that, because you get such dense spatial resolution, the problem with that is that you just get huge data volumes, right? But fiber, that's no way, a detriment, because if you're going to get more resolution, you kind of need to have that more data. But that doesn't mean that you have to maintain and keep all that data. So in this example here, I just kind of want to show that for data storage for 2 kilohertz sampling, 1 meter channel spacing for a 1 kilometer fiber for a week here or for a month here is like 10 terabytes, right? So, but in reality, we can decimate our data quite a bit. Like, not all of the fiber optic is going to be useful. Don't have to put out data at every channel. We can put it out at every other channel. There's ways to decimate in space and time. So for a lot of the projects that we're doing right now, you don't see a lot of high data volume. So it's very, very manageable. And then and this image here on the left here, this plot is just showing that max sampling rate. Some people are curious to know, how can you still sample at 4 kilohertz or 2 kilohertz over a long length of fiber? And essentially, because we pulse the light so fast down the interrogator that there's really no upper threshold to what is going to be useful. We can record for short distances at 10 kilohertz. So we only become kind of limited by the pulse rate of the laser around 50 kilometers or so. But that's, at that point, you're getting degradation in signal quality anyway, just from the pulse size kind of degrading over time. So, and all this is kind of being done, like a lot of companies now are looking to just process data at source. So so DAS can be processed at its location and only triggering the data that you need. So then you can do this all too remotely, so that you don't have to have huge data storage on site, and it all can be processed locally on site. So fewer issues there. And just kind of summing it all up here in this last slide. So this is just from Newcrest Mine here. I took an example from their report, but I just wanted to show all the different applications for DAS in mines that we can potentially use. So we can instrument boreholes in the near surface near open pits for slope stability monitoring and for strain monitoring. We can monitor subsidence in the near surface with using multi-channel analysis of surface waves or tomography or strain. We can monitor from purpose-drilled boreholes for microseismic and strain associated with mine development. So these are permanent boreholes and instrumented with fiber that will stay there for the life of the mine. We can instrument exploration boreholes that are going to be drilled in our mines. So as they're drilled, it's really easy to instrument these. We just put in the grouting pipe when it's going in to grout those boreholes, and we can just strap fiber to it as it's going in. So it takes no time at all. It's quite easy. And we can then use a single interrogator, and we can actually monitor the full infrastructure of the mine as well. A lot of the mines I've been in, you can look up and you can see fiber optic, communications fiber all through the roof of the mine. If we could just somehow get that bolted to the surface of the tunnel, then you could use that then as a dense fiber optic array. So you could use it for strain monitoring and for mitigating rock burst hazards and things like that. But also you could turn the entire tunnel infrastructure into a seismic array and use that for microseismic source locations. So that's it. And so any questions?